In this problem, we're being asked to integrate the rational function x plus 4 over x squared plus 3x plus 2 from 2 to 4. Now, to integrate this, we need to figure out what integration technique we should use. We might be inclined to start with a u sub where we let the denominator be u, but the problem with this is that the derivative of this, our du, would be 2x plus 3. Unfortunately, we don't have 2x plus 3 in the numerator, right? So in this case, I might shift away from doing a u sub, and instead, what I'm inclined to do is, well, because I'm working with a rational function, the question becomes, could I use partial fraction decomposition? Well, hopefully my denominator can be factored down here, and that would work well. Let's go ahead and see if our denominator does factor nicely. So what factors would produce x squared plus 3x plus 2? Well, x times x would produce x squared. 2 only has two factors, 1 and 2. So this would be 1 and 2. And then I need to add up to 3, but multiply to positive 2. Well, these would both be positive. Okay, perfect. So what we've recognized is this rational function, its denominator could be factored into these linear terms, right? These are both linear. They look like lines, y equals kind of mx plus b form, and they're non-repeating. So it would be a great opportunity for us to use our partial fraction decomposition technique where we treat both of these as linear factors that are non-repeating. So we start by writing out our decomposition, integral 2 to 4, a over x plus 1. Again, it's a linear term, so it gets a constant up top and it's non-repeating, so we just do the one factor. And then x plus 2 with a b on top, same logic. Now we need to determine what our a and our b values are, and to do this, we need to create our working equation. So what we see is that taking this, and if we want to set it equal to this, if we can get a common denominator, we could ignore the denominators and just compare the numerators. So in a quick fashion, this should be x plus 4 equals a times x plus 2 plus b times x plus 1. Again, we can get quicker at this as we look in our past videos on partial fraction decomposition, kind of showing all of the logistics behind this. But it's essentially, we just kind of do these terms and we compare it to the numerator. Pretty quick and easy. Now, once we're at this step, you can decide to use one of our two methods to actually solve for the a and b values, right? We have the Heaviside cover-up method, which is, in this case, probably going to be a little bit quicker, or we could do our polynomial mirroring. I'm going to again use Heaviside cover-up method here just because it's a bit quicker. What we do is we strategically choose some x values so that we can cancel out either the a term here or the b term here, and therefore you're left with only one unknown, right? So if you cancel out the b, you would only have a to solve and vice versa. So to cancel out the a term, you would need to let x be negative 2. That way this would go to 0 and we would cancel out, or cover up this term so it's no longer there. X would be negative 2. Over here, x would have to be negative 1 to cancel out this b term. Now what we're going to do is we're going to plug this into our equation and see what we get. When x is negative 2, the left side becomes 2. The right side, this term goes away, and we get negative 2 plus 1, or negative b. That gives us b to be negative 2. From here, we solve for a by plugging in x is negative 1. On the left side, we get negative 1 plus 4, that's 3. Negative 1 plus 2 would be 1a, and then the b would go away. Therefore, a is 3. Now that we know a and b, we're going to plug them into our integral that we were trying to solve up above. So a is 3, b is negative 2. And then we're just going to go ahead and try and evaluate what this is. Note that, of course, these fractions here are going to fit our natural log rule. So it looks like a constant, over x, 1 over x. And we know the integral of 1 over x is natural log absolute value x. So when we integrate this, we would get 3 ln x plus 1 and then minus 2 ln x plus 2, both in absolute values here, and that'll be evaluated 2 to 4. Note how when we did this, technically there would have been a u sub, so u plus 1, or x plus 1 would have been u. Same thing here, we would have done a u sub, but since the derivatives of both of these are just 1, the u sub doesn't really change anything. We don't have to add anything extra in here, and so I'm kind of doing the u sub in my head, right? we want to get good at kind of recognizing, okay, there's no additional terms that need to be done here. I can just use our basic natural log rule. Now, once I'm at this step, of course, we're going to go ahead and plug in. Top bound would be 3 ln 5. I can drop the absolute value now because I'm plugging in a value, and the resulting term is going to be a positive. Minus 2 natural log 4 plus 2 is 6. Again, positive. We'll drop the absolute value. Subtracting 3 ln 2 plus 1 is 3. Minus 2 ln 2 plus 2 is 4. These terms don't really seem like they can simplify very much, but what I do recognize is this term and this term both have a coefficient of 3, and similarly this term and this term have a coefficient of -2. And so what I'm going to do is I'm going to go ahead and combine those. So the terms that have a coefficient of 3, I'm going to go ahead and pull that 3 out, and I'll get natural log of 5 minus natural log of 3. Similarly, with the -2 in front, I'll pull the -2 out. I'll get ln of 6 minus ln of 4. Note that this negative is why I have that negative there. And from here, what we'll do is we'll just combine these together using log rules. So this would be 3 natural log of 5/3 minus 2 natural log of 6/4, which would be 3/2. So that might be a rewrite that I would do. Of course, this is totally sufficient as well. I'd probably drop some of these parentheses and just distribute the negative, but any of those forms would be totally acceptable here.